Hello, this is Dr. Waiters. I am going to do experiment 12, acid and base titration. Due to the pandemic, we are not allowed to come to the lab, so we are going to do them online. So I am videoing this by myself, so give me a break on the comments. All right. So first thing we're going to do is we're going to prepare our acid and base solutions. And in number 1, if you are following along, which you should be, experiment 12, it says to prepare approximately 1 liter of approximately 0.06 molar NaOH. All right, it also says to make 0.04 molar HCl approximately, and in approximately 1 liter. So the approximately's make this very simple. We are not going to measure the water. We will measure the acid to make sure we have an approximate correct solution. We're going to do the titrations to get the actual concentrations to 4 significant figures. All right. So on the board I have the calculations. I will show you the calculations. All right. So if you can see this, to make about 0.06 molar NaOH, from 6 molar NaOH we do a dilution. MV is equal to MV. So we want to make 0.06 molar and we want to make approximately 1 liter. I have converted the 1 liter into 1,000 milliliters, and that is equal to your 6 molar at what volume? So that is the question. What volume of the 6 molar do we need? We divide both sides by 6 and we get the answer of 10 milliliters of 6 molar NaOH. All right, and so again, it's all approximate. So fill a 1 liter bottle with the ionized water. So what you're going to do is you're going to put in your 10 mils and fill the bottle with deionized water, and I will show you how to do that. You will not have to do it. I'm going to do it. All right. For the calculation for your HCl, again, it's a dilution. We're going to make 1 liter of 0.04 molar from 6 molar HCl. So again, the dilution equation, MV is equal to MV. This time we want to make 0.04 molar. We want to make 1 liter again, which I've converted to 1,000 milliliters, from 6 molar HCl. Divide both sides by 6 and you get the volume is 6.7 mils of 6 molar HCl. We add that to a bottle and then we fill it with deionized water. So I will show you this setup. All right, so the setup is here. All right, so I have my 6 molar hydrochloric acid. All right, so I'm going to take 6.7 mils, measure it out with my 10 mil graduated cylinder. I'm going to pour it into my glass bottle for the acid, and then I'm going to go over to the deionized water and fill the bottle. I am not going to measure the water. I'm just going to fill the bottle with deionized water. And then over here, I will do the same thing, except with my 6 molar NaOH, I'm going to use 10 mils in my 10 mil graduated cylinder. I'm going to pour it into the plastic bottle for the base, and then I will fill that bottle with deionized water. Again, I am not going to measure the water. So I will do that, and then we will continue. Okay, I've made my 2 solutions. Now in number 2, it says to carefully clean both of your 25 mil burettes. So here I have the 2 25 mil burettes. Now I always have the acid on the left and I always have the base on the right. It's alphabetical order A, B, so I do not have to label anything. I know that my acid's always on the left and on the right. So what I did with my acid and base is to fill up the burette. It's much easier if you put it in a beaker, and so I put my solutions in beakers so I can add it to the burette much simpler. All right, and it says to thrice rinse. That just means rinse it 3 times. So these could be contaminated with somebody else's solution from a previous year, a previous lab. All right, and so we don't have to spend a lot of time cleaning it. We just have to make sure that anything in there is now this in there. All right, so if it is wet with this solution, that is fine. If it is wet with water, it's going to dilute it, and that would ruin your first run. All right, so we're going to thrice rinse it. So all that means is make sure your stopcock is closed. Get a little closer here. All right, and so you have your stopcock that will open and it will go straight through, and this is closed. All right, so we're gonna pour our solution in here. So it says put in about 5 mils and to rinse it. And so we're going to make sure that all the walls of the burette touch this liquid. And these solutions are very dilute solutions, and so we can pour them down the drain. For now, I will just put them in another beaker here. And so you can see that we're just going to rinse them. All right, so that's the first rinse. And here is the second rinse. We want to definitely rinse out the bottom as well. So we want to open the stopcock and let it go through the bottom. All right, so we're rinsing out both the bottom and rinsing it out the top. All right, so that's the second. All right, and then here is the third. All right, so we have rinsed that out. Rinse this out. All right, so now it is wet, but it is wet with our solution. And so we will then fill the burette. So once we've thrice rinsed it, now we can fill it up to the top. All right, so I always go past the 0 mark. So this is a burette. When you fill a burette, it reads 0. All right, and so I filled it all the way up because there's air in here. And so I have to open this up and get rid of all of this air. And so I'm going to open it up, and all the air bubbles are now out. I have to bring it down to put it in the reading. So when you have a burette, it has to always be, the liquid is up here now. It has to be between the 0 and the 25. It should never be above 0 when you're titrating. It should never go below the 25. All right, and so I'm going to bring it down to 0. All right, so I have it 0. Now a burette, you read a burette to 2 decimal places. And so I'm going to bring this down a little bit. I don't want it to be at 0. I want to read it. All right, and so when you read it, it is at 0 here, and so it is slightly below the 0. And so it's a very strange scale. It goes from 25 up to 0. So this is going to read, and I'm going to put it back into my burette stand. All right, and so this reads 0.15. And so our initial reading for our acid is 0.15. And that is milliliters in your cylinder. So I will do that with the base, and then I will come back to you after that. All right, I filled the NaOH burette up, and I got rid of the air bubbles down here. But as you may be able to see, there are some air bubbles on the sides. Now you have to get rid of the air bubbles on the sides, so I'm going to tap it with a, I don't know if you can see the air bubbles coming up, with just a rubber stopper on a glass rod. And so I'm loosening the air bubbles, getting rid of all of the big air bubbles before I put it back on the burette stand. Alright, so the ones that, there's going to be a couple, oh there they go, okay. Alright, good. Alright, so I got rid of most of the air bubbles. Oh, there goes another one. Alright, so now we're ready to take our initial reading for our NaOH. .52. And so your initial volume is 0.52 for your NaOH. All right, so now we are on number 3. Deliver 20 to 25 mils of HCl into a clean, but maybe wet, Erlenmeyer flask. So I have my 125 mil Erlenmeyer flask, and I'm going to put in some acid. So when I'm going to put in the acid, it's underneath the stopcock here. I'm starting at, again, 0.15 for my HCl, and then I'm going to put in about 20 to 25. So I want to go down until it's down to the 20 mark. And again, it doesn't matter how much you add. I'm going to add about 20. And so when it gets down to 20, I will stop adding the HCl. So when it says deliver, that means add the solution into your volumetric flask. I may have to get a new burette for the acid. It's a little slow. Alright, so I have stopped it, and the reading for your acid is 20.48. So your volume is 20.48 for your HCl. Now there is a drip, you probably can't see it, but there's a drip on the end. It has counted that drip. That drip must be put in, and so you tilt it to the side to put that in. Alright, and so now it says to add about 15 mils of deionized water, which I have right here. Alright, and so we're going to add 15 mils of deionized water. Alright, so I filled up my 100 mil graduated cylinder with deionized water, so I don't have to fill it up multiple times. So 15 mils, I'm starting at 100, I'm going to go down to 85. And again, this is deionized water, which means that it's pure water. So it doesn't matter how much we add, but we want to have an approximate amount. 15 mils has been added. Alright. So I added 15 mils of deionized water. Now I have to add an indicator before I do my titration. 5 drops of phenolphthalein. So phenolphthalein is my indicator. So in acid, the phenolphthalein is colorless. All right? When it is at a pH of 8.2-ish, it'll start turning a light pink. Alright, so 5 drops of my phenolphthalein. Alright, so now I'm ready to do my titration. So I have my acid in here, and now I'm going to add my base. And when it is neutral, it is going to turn a light pink. Actually, it'll be a slightly basic. Now, when you're doing a titration, a color change is an estimation of your equivalence point. Alright, when you're doing a titration, it's called the end point. That's when you stop adding the acid. It is not the exact equivalence point. It is an excellent estimation of the equivalence point. Alright, so I'm going to add my base. Alright, let's get this a little closer. Alright, so you probably can't see, but when it drips in here, I have a white background, maybe that would help. When it drips in here, you have a light pink color. I'm trying to give a white background so maybe you can see some of that color. All right, and so there is a pink color building up. All right, but when you swirl, it goes away. What we're looking for is at the end point, it is going to take one drop of your base to turn it a light pink and to stay light pink. Now we can do a back titration here because we have our acid right here. So if we get it a dark pink, we can add acid and go back to colorless and then add our NaOH to get it a light pink. And then we will take our final readings once we have our equivalence points. It looks like we're getting very close. So the pink is hanging on, and now the pink hasn't disappeared. So now we will have to do a back titration. All right, and so a back titration means we have to add a little bit of acid, although this is a pretty good endpoint. All right, so we may just stick with this one. So this is a light pink, all right, and it's staying light pink as you swirl it. All right, and so, well, actually I'm not sure if it stayed long enough. Let's add another drop. All right, and so we add another drop. So it has to stay light pink for 30 seconds. All right, and so as we swirl it, it has to stay the pink color for 30 seconds. If it disappears like it did last time, that means we need a little bit more of our base. And it looks like this time it is going to stick with us. So we know we're right at the point. It was no color, I added one drop, and now it is staying a light pink. And so we are at the equivalence point. And so now we didn't have to add any more acid. This is a good endpoint. All right, and so we get our final volume of our base. And our final volume of our base is 11.62 milliliters. All right, I am going to clean this up and get ready for the next titration. All right, I am set up for my next titration, which is to do a check of the water. So in here I just have 50 mils of deionized water with phenolphthalein indicator. All right, and so if this takes more than a few drops, then there is something wrong with our deionized water for it to turn pink. All right, so I'm going to add this very slowly. It should turn pink immediately. Deionized water should be neutral. As soon as we add NaOH, it should turn pink. And it does. One drop turned it to a pink. All right, so that's something you always need to do to make sure that your deionized water is at a pH of 7. And it is. One drop turned it pink, and so our water is good to go. I will set up for the next titration. All right, the next titration is going to be with KHP. Here we have 2 bottles of KHP. One on the left here is pure KHP. It's 100% KHP. The one on the right is an unknown KHP. We are going to calculate the percentage of this KHP by doing a titration. The unknown number in this case is number 22. All right, and so we have our 4 decimal place balance. We have our weigh boats, and we are going to add 0.17 to 0.18 grams of pure KHP. Now KHP is a compound called, can we see this here? We go. Potassium hydrogen phthalate. So phthalate is an organic compound. You do not need to know the structure of potassium hydrogen phthalate. Feel free to look it up if you want. But this is a potassium salt. So all salts of potassium are soluble. And so when we write our net ionic, this is HP minus. P is just a symbol for the phthalate. So it is, again, an organic compound. The molar mass is given for KHP. The molar mass is 204.23 grams per mole. That is what we will need to know. All right. And it has 1 H, KHP. And so this is our acid. It is a monoprotic acid, a 1 hydrogen acid. Again, important to know when we do our balanced chemical reaction. All right, and so I'm going to weigh this out for you, and we will then do our titration with a solid. This is a solid that I'm going to weigh out. I'm going to dissolve it in deionized water, and then we're going to titrate it. So I will get that prepared for you, and we will run this titration. All right, we are ready for our KHP titration. Let's go this way. I have added to the flask 0.1741 grams of KHP. This is the 100% KHP. And I added 50 mils of deionized water. KHP is a solid, and I am still in the process of dissolving it. You can see some solid on the bottom. All right, and so I'm going to keep swirling to dissolve the KHP. So this is an acid solution. KHP, again, is a monoprotic acid. All right, and so we're going to add our base from our burette, and it's going to turn a light pink because I added the 5 drops of phenolphthalein. And you will know if you did not add the drops of phenolphthalein because it will never turn pink. All right, and you should know this right away. As soon as a drop hits, you're going to see some pink. All right, maybe not on the camera, but I will see some pink, so I know that the phenolphthalein is in there. All right, so we are ready to do this titration. Now we need our initial volume for the NaOH, and that is 0.31 milliliters. And so you have 0.31 milliliters for our initial concentration of our NaOH. All right, so now we are ready to do the titration. Let's see if I can get a white background to see this color. All right. And here you do not want to pass up the endpoint. It is unlike the last titration. If I passed it up, I could have added some acid. I can do that this time, but that's a lot more calculations, and we don't want to do that. So we want to make sure that we are doing this titration at a slow drop rate so that we do not pass up the endpoint. If we pass up the endpoint, we're going to have to reweigh our KHP and do another run. So I have added the KHP. I don't know if you can see it on the film, but there is some pink as soon as it hits. All right. And again, it has to stay pink for 30 seconds while swirling the flask. And as I'm swirling, I can see how long the pink is lasting. If the pink lasts a long time, I know I'm getting very close to the end point, and I will slow it down. But even at this rate, it is a pretty slow drip rate. If it passes up, it'll pass it up by a drop, and we are not going to be that specific with the concentration of the NaOH. Alright, so now the pink is lasting a lot longer, and so I'm going to slow it down. I do not want to pass up this end point. And also during a titration, if you see some pink on the sides, you have your squirt bottle of deionized water. And you can add as much deionized water. Again, the deionized water, it is a very perfect pH neutral. It is not going to affect our titration. We are not adding acid, we're not adding base, it is completely neutral. And so any splashes that come up, we can rinse them down with a squirt of deionized water. Getting very close. I think that might do it. One drop, turned it pink. Now we just have to rinse it down and make sure it stays pink for 30 seconds. And since we saw one drop change that color, we know that this is a very good titration. It's going to give us very good results. Alright, still a light pink. After one drop changed it from colorless to pink, and it has stayed light pink for 30 seconds, and this is our endpoint. So now we just need the volume of our NaOH, and so we read the volume of the NaOH, and it is 13.11. So 13.11 milliliters is our final volume for our NaOH. Alright, I will get the unknown KHP ready for our final titration for this experiment. Okay, we're ready for our final titration for experiment 12, the acid-base titration. I weighed out 0.4694 grams of the unknown KHP, and that is unknown number 22. Alright, again, that's a solid. I am dissolving the solid in 50 mils of deionized water. I added the 5 drops of phenolphthalein, and we need to get our initial reading for our NaOH. Alright, and so the initial reading for our NaOH is 0.39. So 0.39 milliliters is our initial volume for the NaOH. Again, we do not want to pass up this endpoint, so we want to add this relatively slowly. We'll let it drip in. We see some pink as soon as it hits. We know we've added our phenolphthalein. All right. Again, we can go relatively fast until we see the pink staying around for a long period of time, and then we will slow it down. But again, I'm going at a very slow rate even now. So even if it were to change, we would only be off by 1 drop. So you always do your titrations very slowly. And you swirl it as it's going in. You could do the two-hand approach. If I do the two-hand approach, no one could see what's going on in our titration. So one hand getting ready to turn off the stopcock while the other hand will swirl the flask. The color is starting to linger a little longer. We're getting closer. All right, so let's slow it down a little bit. Again, we want it to change when 1 drop hits. That would be the ideal case. 1 drip, and it goes from colorless to a light pink. All right, so now the drips are going in much slower. All right, that's it. So now we will squirt it down. And then we will swirl it and make sure it stays a light pink for 30 seconds. 1 drop, changed it from no color to a pink color that is remaining. And again, if we swirl it for 30 seconds and it remains which it looks like it will, then we have our solution. All right, so it is a light pink. It stayed for 30 seconds. I'm pouring it into my beaker back here. The endpoint beaker. All right, and so now all we need is our final volume. And the final volume for this one is 11.59 milliliters. 11.59. All right, that is our final titration for experiment 12. I am going to go through the calculations next. I'm going to clean this up and go through some calculations. Well, as they say, chemistry and cooking are very similar, but in chemistry, you never lick the spoon. But sometimes you just can't help but wonder, what does this neutral phenolphthalein solution taste like? So sometimes you just have to do an experiment. Tastes a lot like fruit punch. All right, the calculations. To calculate the concentration of your NaOH, you use the titration equation for a solid acid. KHP was a solid acid, and an aqueous base. We had a liquid NaOH concentration of your base. All right, and so your acid equals base for your titration. Now the titration equation is for a solid. You're going to take the mass of your acid, divide by the molar mass of the acid, and divide that by the coefficient of your acid. And for the base, since it is a solution and we have a molarity, you will take the molarity of your base times the volume of your base divided by the coefficient of the base. All right, so the net ionic equation. So as I said before, potassium, all potassium salts are soluble and all sodium salts are soluble. So when you are reacting KHP with NaOH, the reaction is HP minus plus OH minus yields water and P minus 2. So acid, base yields salt and water. All right, and so for the net ionic, we do not include the potassium or the sodium. All right, so for our lab, all right, we needed to find this reaction in order to find the coefficients. So your coefficients of both the acid and the base are 1. So now we put in the mass of our acid. So we followed along. You have in your data sheet the mass of the KHP, of the pure KHP, divided by the molar mass of KHP, which is also given as 204.23. And then the coefficient in our balanced reaction is 1 for the acid. For the base, molarity of NaOH, that is what we are calculating. That is what we do not know. All right, but we do know the volume of NaOH. But that volume on the burette is in milliliters. Make sure that you use the volume of NaOH in liters. All right, and then again the coefficient is 1. And so when you take your mass, divide by your molar mass, that's going to give you moles. To solve for the molarity of NaOH, you need to divide both sides by your volume of NaOH in liters, and that then will give you moles per liter, which is the molarity of your NaOH. Now to calculate your percent KHP. So to calculate the percent KHP in the unknown, you use the same titration equation. We use the same reaction. It is then the same equation. So here it is the mass of KHP, and now I'm going to put in here pure KHP. The unknown is not pure KHP. The unknown has other things in it. All right, and so this is the mass of pure KHP divided by the molar mass of KHP, which is 204.23. And the coefficient of KHP, which we have there as a 1. And then again, we have our base, which is a solution. We added the base as a solution. we added our acid as a solid. The unknown was a solid. All right, and so your molarity of your NaOH that we now know because we just calculated it, and then the volume of NaOH again is how much that we used for our titration of our unknown. Again, must be in liters because of the units. Molarity is moles per liter. You have to multiply that by liters in order to get moles. And then your coefficient of your NaOH from our balanced chemical reaction is a 1. All right. So again, we now know the molarity of NaOH from our previous calculation, but we do not know how much of that KHP was pure KHP. And so we have to solve for the mass of pure KHP in that equation. Now once you have the mass of pure KHP, to get the percent KHP, you take always 4%, part over whole times 100. All right, now the part is the mass of pure KHP. How much of the unknown was pure KHP? So that is the part. The whole is the mass of the entire sample of your unknown KHP. And then multiply by 100 and you will have your answer. And that is how you will do the calculations. Note that if you have an experiment that shows that you are to do these things 3 times, we are only going to do each one of them 1 time. You're not graded on how close you are to the correct answer because I did the experiment for you. And so we're not going to be calculating any averages or standard deviations. So all we need is the RAB value, we need the molarity of the NaOH, and we need the percent KHP in the unknown. We will also need the molarity of the HCl. Those are the things that we are calculating. All right, we're going to end this experiment. Thank you.